Hi, everybody. It's great to see so many people who are interested in learning a little bit more about quantum computing. So before we get started in today's session, I want to take a few moments together to imagine some big things that we would potentially like to change about the world. So one huge thing that we could hope for would be to have much more efficient, much more cost-effective food production so that we could potentially solve a big problem like world hunger. That would be incredible. Another really exciting thing could be to have much better healthcare solutions, much better diagnostic tools for doctors so that we could identify more disease earlier. And another thing that we might hope for is a methodology to obtain optimal solutions for some of our most complex and important business decisions. This exciting potential future is one that could be brought closer by quantum computing. I'm Michael Beverland. This is my colleague here, Bettina Heim. And today we're going to tell you about quantum computing. We're going to explain a little bit about how it works. We're going to point out some key applications that quantum will help with. And most importantly, we're going to introduce you to Microsoft's Quantum Development Kit, which is the tool which will allow you to enable yourself to take advantage of the quantum revolution as it comes. Does anybody recognize this picture? This is the ENIAC computing machine. This was completed in 1946 at the University of Pennsylvania, and it's one of the world's first general-purpose computers. The people shown in this picture, the programmers of the day, I like to think that they could probably already sense that these machines and others like them were going to change the world forever. And in quantum computing, we feel kind of similarly. We feel that we are currently on the precipice of huge change in quantum computing. We can already point out a few key problems that quantum computers will help to solve. And yet, a little bit like the people in this picture, we can probably only identify the tip of the iceberg at the minute. We really believe that the solutions, although important that we can already identify, are really only a very few among what is really potentially possible with quantum computing. So today, I'm going to walk through some of those problems in the tip of that iceberg. So fast forward to today, and this is the Summit supercomputer in Oak Ridge National Labs. This is the fastest supercomputer in the world today. And the ENIAC that I showed in the previous slide was able to perform about 5,000 operations per second. The Summit can perform 200 petaflops, which is 200 million billion operations per second. So we've really come a long way since the ENIAC. Despite this, there are still some problems that we cannot solve with current computing technology. An important example is understanding the detailed chemical structure of certain molecules. The molecule on the left here, the caffeine molecule, is a molecule that can be understood with current supercomputing technology. On the other hand, the molecule on the right, which is an iron-molybdenum complex, let's call it FOMOCO for short, is a molecule which is slightly bigger and has some slightly more complex properties, making it a little bit more difficult to simulate. In fact, our current supercomputers are very far from simulating this molecule. So what is it about molecules that makes them difficult to simulate? Well, the problem is that they run according to the rules of quantum mechanics. And quantum mechanics, although we understand the rules and we can write down the rules of quantum mechanics, is very, very difficult to replicate on conventional computing technology. It scales exponentially. So if you have a particular molecule that you're simulating, if you add just one more atom to that molecule, you need to double the resources required to simulate it. And very quickly, it becomes impossible to simulate even a relatively small molecule. So this molecule here, this FOMOCO molecule, we'll come back to it a little later, but it's really key for nitrogen fixation, a process by which nature creates ammonia. The frustration of physicists and scientists at not being able to simulate molecules was actually one of the things that led to the very conception of the quantum computer in the first place. Nobel Prize-winning physicist Richard Feynman in the early 80s was thinking about similar ideas to this. And essentially, paraphrasing, he asked the following question. If these really small quantum mechanical systems, molecules, are doing something so complicated that our most powerful supercomputers have no hope at replicating their behavior, maybe we should be using the small molecules as the computers. Maybe we should be building our computers to harness the quantum mechanical effects that make those molecules so difficult to simulate. And this was a brilliant idea. Of course, if you were able to build a computer which harnessed quantum mechanics, a quantum computer, then you would be able to understand molecules like FOMOCO that we showed previously. You would also be able to understand other physics problems. For example, you could potentially design new quantum materials. We could understand high-temperature superconductors, which would potentially allow us to build loss-free power lines. There are a multitude of applications in industry which this could be useful for. And probably most interesting to Richard Feynman as a physicist was you could also understand the very nature of the smallest particles themselves, quarks. That was probably really his core motivation for thinking about this. But in the early 80s, when Feynman came up with this idea, he also speculated maybe there are some other problems that a quantum computer would be able to solve, some problems that have nothing to do with physics or quantum mechanics. And a little over 10 years later, that question that Feynman asked was answered in the affirmative. Peter Shor in 1994 came up with the quantum algorithm for factoring. So you probably remember factoring from middle school. It's that simple problem where you have number, say 15, and you have to split it into its smallest prime factors. So 15 is 3 times 5, for example. 22 is 2 times 11. And it turns out that this problem gets difficult for conventional computing technology as the length of the number that you're trying to factor gets big. So this curve here on the graph shows along the x-axis, we have the number of bits, so the length of the number of digits, and the number we're trying to factor. And on the y-axis, we show the total amount of time that would be required to perform the factoring if you had 100 conventional computers at your disposal. So you can see those numbers along the y-axis get very big very quickly. And actually, it turns out that this is really important. It turns out it's a really good thing that this number, that the amount of time to factor gets big so quickly. The reason for that is because factoring is a key component of almost all of the world's encryption that happens today. The RSA scheme, every time you buy a pair of shoes, for example, on the internet, probably the RSA encryption scheme is protecting your purchase, protecting your financial details as you buy your shoes. And that RSA scheme is based on factoring. So, for example, the RSA scheme could use about a 2,000-digit number to protect your purchase. And you should be rest assured then that a hacker with 100 conventional computers would require about 1 billion years to access your financial information. So that's great. But with Shor's algorithm, a quantum computer, a relatively modest quantum computer that we would like to see built in the future, would be able to perform this factoring algorithm very quickly. So potentially in a day or less. And so this is kind of a very scary prospect, that most of our current encryption is actually based on something that quantum computers could hack relatively easily. And it's something that we really should and are currently worried about. And there are researchers at Microsoft and across the globe working to replace our current encryption schemes with something which is quantum safe. So what else is out there? What other problems is quantum computing really powerful for solving? Well, there are lots of different areas that are current areas of active research. And things that we can pick out are, well, we just saw an example of security, where if you had a quantum computer, you could hack security. You could overcome our current encryption methods. But there are also other forms of security which are much better with quantum computing. For example, you can have provably secure communication with quantum, something that you cannot achieve without it. There are also, as Feynman pointed out, chemical applications where we can understand certain molecules which are very important in industry. And materials. Earlier, I mentioned briefly loss-free power lines, but there are other important material applications such as better battery technology and smart materials. And then, of course, there's the broad area, which is a very hot area of research at the minute, of machine learning, where you can find new solutions to complex problems, optimization problems. These are areas of active research in quantum computing as well, where we believe that we will find many areas of speed up. So I'd like to take you through a case study, an example of one of these application areas. This area is the problem of ammonia production. So ammonia, you've probably heard of it in the context of household cleaners, but ammonia is also used for fertilizer. It's the main ingredient for fertilizer. And the ammonia business is huge. It's approximately a $50 billion a year business. And the use in fertilizer is really the primary use of the output of ammonia. So it's really a key part of the food cycle. Fertilizer, of course, has a massive impact on the entire global food system. So the way that we're currently producing ammonia is from natural gas through a process known as the Haber process. The Haber process has been around for about 100 years, and even though it's quite old, it's very successful. It is widely regarded as one of the most important industrial chemical processes that exists. Unfortunately, it's quite expensive. It requires about 2% of the entire globe's annual production of natural gas just to produce ammonia through the Haber process. And it's also a very high temperature and pressure process. It occurs at hundreds of atmospheres of pressure and about 1,000 Fahrenheit. So it's really very expensive because of all of the infrastructure that you need to build that, to implement it. And because it's such a huge industry with such big impact for the food system, it's clearly a very high value to improve it. So you might ask, well, if it hasn't really changed in 100 years, if the fundamental process is still the same, maybe you cannot improve upon it. But we know that the ammonia production process can be improved because nature is essentially doing the same thing for free right now outside this building. Bacteria are able to take nitrogen directly from the air instead of using natural gas, And instead of using high temperature and pressure, they can do it at ambient temperature and pressure. They're doing it outside. So how does nature do this? What is nature doing that we have not been able to do? Well, nature has a biological catalyst, an enzyme, nitrogenase. And the key part of that enzyme is precisely the FOMOCO complex that we saw earlier. And we really do not have a good understanding of how that catalysis process works. If we could understand it, then we would hope to be able to replicate it or do something very similar and build that out in industry. A quantum computer would allow us to understand that complex. A relatively small one of just a few hundred qubits should be enough. Before I move on, there are a number of other problems. I mean, that was one example, and I think a very important one, but there are a number of other examples that you can imagine that would be extremely important. Imagine, for example, if we were able to find a catalyst for carbon sequestration, so that we could remove carbon dioxide from the atmosphere and mitigate some of the effects of global warming. That's another process that we don't understand as well as we would like, and we would hope to be able to understand better with the power of quantum computers. So where does this extra power come from? Why is quantum so different? Well, you could make the argument that regular computers, conventional computers, haven't changed for the last 4,500 years. The fundamental principles. Okay, sure, the actual technology, the implementation has changed a lot. Now we have the transistor, which is clearly very, very powerful and fast. But the very concept of how information is stored and used, left, right, 1, 0, if, or, these binary processes have really not changed at the fundamental level. And quantum mechanics is different from that. It's really fundamentally different. So let's take a little bit of a deep dive into what we mean by that, in what way it's different. This part of the talk will be slightly more technical than the other parts, but I think it's interesting and important to really get a feel for how quantum is different. So on the left, it's going to be what we already know, conventional stuff, and on the right is the quantum case. So the fundamental building block of a conventional computer is the bit. The bit takes two possible values, 0 and 1. And essentially everything, every data file that you've ever stored, everything that is kept on any kind of computational device is, at the very fundamental level, broken down into bits. Many, many of them, of course, but still broken into bits. And we can have a nice pictorial representation of these bits. They're like switches. So we take two possible cases. We either have this rectangle, this light blue rectangle on the left, or we have this dark blue rectangle on the right. These are the two options for the bit. And the quantum version of the bit is the qubit, the quantum bit. And like the conventional bit, the quantum bit can have two possible values. It can take the value 0 or 1. But there are other possible values for the bit too. There are other possible states. The quantum bit, the qubit, can take what we call superposition states, where it is in fact in two bits, both 0 and 1, in some sense at the same time. Moreover, the amount which is in 0 and the amount which is in 1 does not have to be equal, as I showed before. It can really be any amount. So there are a huge number of possible different states for the qubit. And that's the first difference that I would like to draw to everybody's attention. But to really see how this becomes relevant, we need to think a little bit about a quantum program. So a conventional program, at its fundamental level, is really just a changing of bits into one another. A very simple example of a program will be the following one. Imagine a program where you just have 2 bits and you change the value of the second bit. So clearly, if you have an input and output of this program, if the input happened to be 0, 0, then the second bit would become 1, and you would output 0, 1. Or if the input were 1, 1, you would output 1, 0. The second bit is changed. And now let's think about a very similar program, essentially the same one, but run on a quantum computer. But now we have to remember that quantum states can have multiple bits at the same time. So before, when we considered a single bit, we just had 0 or 1. Now we have 2 bits. So our 2-qubit state can have contributions from all 4 possibilities of 2 bits. And then when our quantum program runs, the same one as before, the swapping of the second bit, we simultaneously act on all parts of the state so that all of the bit strings are acted upon simultaneously. And we can ask, I just drew a picture of this. I clearly can represent it on a piece of paper with my hand. It's something that we can understand in this way. Can we simulate this behavior with a conventional computer? We can simulate this behavior with a conventional computer. To follow what a quantum computer would do in a program such as this, we could simply follow exactly what happens to all of the bit strings. That's possible. And so in this case, in order to simulate a 2-qubit quantum program, we would have to follow what happens to all 4 bit strings. And if we use this same approach to simulate larger programs, then when we go from 2 qubits and 4 bit strings up to 3 qubits, there are, of course, 8 bit strings that we have to follow now. And this starts to grow pretty quickly. If you wanted to simulate a program in this way of 20 qubits, then that would involve about 16 megabytes of memory just to follow all of those different bit strings that make up the state. And you could probably do that on your cell phone. If you wanted to follow a 30-qubit computation, then you would start needing about 16 gigabytes of memory. And that you can do on your laptop, probably. And if you go up to 50 qubits, that's getting to the boundary of what we can actually do today. So that's now this machine that I showed at the start. That's the petabyte range of memory. And you would need a current supercomputer to do that. But really, we want to build much bigger machines than this. Our scalable quantum applications will eventually involve hundreds, thousands of qubits more. So this number 50 here should be seen as a very small number. And already, when we have 250 qubits, that would require us to, if we wanted to simulate in this way, that would require us to follow as many different bit strings as there are atoms in the universe. And that's kind of a very compelling thought. It really means if we were to have this thought experiment where we were to build the biggest computer that you can ever possibly imagine, build a computer built out of the entire universe, a conventional computer of that size still wouldn't be able to simulate a quantum computer of just a few hundred qubits in this way. So there's really a lot going on there. So how does a quantum program take advantage? How do we actually use this incredible power? Well, the ways that we understand quantum algorithms are quite hard to visualize sometimes. But I quite like this example of an optimization problem. It allows us to get some sense of one way that a quantum computer can take advantage of this extra power. So in an optimization problem, the goal is to find, there might be many potential solutions for some problem, and you want to find the very best one. And in this pictorial representation of that, we can imagine some undulating surface, where the goal of this optimization problem is to find the minimum of that surface. And you can see from the picture here, the left picture, that just by looking at it, we can tell that there's this very deep kind of valley on the right. It's a very narrow, deep hole. So the true solution to this optimization problem would be the bottom of that narrow hole there. And the way that a non-quantum optimization algorithm would attempt to solve this is it would really sample different locations on the surface and try to identify what the value is, what the height is there. And it would look around somehow locally, trying to find what the bottom was. So you can see a little video representation here. The ball represents the current solution that the optimizer has found, and it's wandering around, and it can see this low, broad valley on the left of the image, and it kind of gets trapped there. So because the true solution is in this very narrow well, it hasn't seen it. It hasn't wandered over to that part of the space, and so unfortunately the conventional algorithm failed in this case to find the optimal solution. So how does the quantum case work? Well, one approach to performing quantum optimization is to use the process that we talked about before, where the quantum state has contributions from all possible configurations. So here, what we see on the right is we actually start with the surface as a flat surface, and we slowly are going to stretch the surface so that it comes into the same form as the picture on the left. And initially, the quantum state, you'll see it once I start the animation, the quantum state will be smeared over everything. But as time goes on, as the surface is pulled deeper and deeper, the proportion of the quantum state which is over the low points in the surface become larger. And so as the very deep well is pulled down, eventually all of the quantum state is concentrated around that well. And so the quantum algorithm is not vulnerable in the same way as the conventional algorithm to getting trapped in these local minima. And this actually highlights something that I think is really exciting and really important about our current quantum computing developments. We can actually learn some lessons from how the quantum algorithms operate and pull out pieces of that which can be implemented currently on conventional computers. So this approach we call quantum-inspired algorithms. And an example of this is quantum-inspired optimization algorithms, where we take this idea that the classical algorithm that you saw before would get trapped in a local minima, whereas the quantum would not. And the quantum is capable of tunneling the density of the state, which slowly went over to the deep well on the right. We call that process tunneling. That quantum process is something that we can simulate to an extent on a conventional computer by adapting our current algorithms for optimization. So developing these new quantum-inspired optimization algorithms, we can actually solve problems today on current hardware with some quantum ideas built in. And one particular case study that I'd like to point you towards is in the space of magnetic resonance imaging. So I'm sure all heard of MRI in hospitals. It's a very useful tool for diagnosis. It allows for non-invasive examining of the entire human body. And it's really fantastic. It's been around for 50 years, and it's very successful. Although there are some drawbacks to current MRI technology and to the MRI that we've had for the past 50 years. It's very expensive to build and to run. It's quite slow, and although it's relatively accurate, it's still not as accurate as we would like. And so there are certain tissue types that cannot be distinguished, and noise that can cause for false positives, for example, in diagnosis. And this slow comment might look a little innocuous, but I actually visited recently the MRI group. I'll talk to them in a few moments at Case Western. And when you really see patients, especially children, young children cancer patients going into MRI machines, it's very difficult to see the process, because some of these scans, some of the more accurate scans, require 30 minutes of no movement. And for adults, that's difficult. It's very hard to get an adult to sit still for that amount of time. I challenge you to do it even for a minute right now. You really can't move during the scans. And for the kids, for some of the kids, they sedate them. They have to sedate them so that they don't move around. And it's, for young kids and anybody with serious illness, it's a difficult thing to put somebody through. And it would be really amazing and quite transformative to have faster scans. A really key development in recent times, just a few years ago, was the introduction of magnetic resonance fingerprinting. So this leverages the MRI technology that already exists and uses it in an innovative new way, where each tissue is assigned a unique fingerprint. Essentially, the scans are done very quickly, and you can identify much more accurately the different tissue types than you were able to in MRI. However, it's still possible to develop this technology much more. MRI fingerprinting is really a new area that has just begun, and there's a lot of potential to improve it. And the problem with that is that the way that these fingerprints are generated that allow you to identify different tissues is through a complex sequence of pulses that are applied as a part of the MRI. And the search space of those pulses is so huge that it's really an impossible space to search exhaustively. So it's a really good avenue to explore with our new quantum-inspired optimization techniques. And we've been working with the team at Case Western Reserve University, Dr. Mark Griswold and his colleagues, to try and develop this technology. And if I can, I'd like to show a quick video from our partners over at Case.
Modern healthcare today is really based on imaging. In the area of MRI scanners, we've developed a technology here called magnetic resonance fingerprinting that really allows us to take a quantitative picture of the patient's body. Microsoft is providing optimized quantum-inspired algorithms to really solve our hard problems, using them to make MRI faster, cheaper, and more efficient to help people all over the world with this technology.
Microsoft and Case Western Reserve are working together to push the forefront of healthcare technology using algorithms that look at the world in a quantum way. We can go much, much faster than any classical algorithm that's been out there to date.
These quantum-inspired algorithms are giving us a window into a future that we just didn't think about before. And we want to use that power to find diagnoses and treatments that mankind just has not been able to come up with yet.
Quantum computing is going to allow us to solve problems that we never thought we could. This quantum-type thinking is going to open new doors that we haven't had before.
These quantum computers will be in our Azure data center. This is the ultimate intelligent cloud. We are going to be able to make profound impacts in the world with quantum computing, whether it's healthcare, whether it's climate change, whether it's food production.
And I just can't wait to see the impact that this is going to make on people's lives.
That's actually a project that I'm personally working on, and I'm really excited about it. I think the potential there is huge to impact people's lives, and it's really great to be a part of something like that. So we've seen a little bit about how quantum computers work. We've seen what they can potentially be used for when we've been able to reach full scale. And we've seen some of the things that we're already doing today by taking lessons from quantum algorithms and applying those to develop quantum-inspired algorithms. So what's Microsoft's overall approach to build up this quantum program? Well, at the very base, we of course need quantum hardware. And it's really crucial to build scalable, reliable hardware. And our approach to that is to build topological qubits, which really have reliability designed in at their core. These qubits, you can see actually a picture of a dilution refrigerator on the left of this slide. These qubits are stored at very low temperatures. So in order to be able to control them, we need revolutionary new approaches to have hardware control that operate at those low temperatures. And in order to enable everybody to take advantage of these quantum applications and to build them, we have the Quantum Development Kit. This is a really exciting way that you can get started today and start using quantum computing approaches and build out your solutions in quantum. And with that, I'll hand over to my colleague Bettina, who's going to talk to the Quantum Development Kit. Thanks.
Thank you, Michael. So as you've heard from Michael, our mission at Microsoft is to build a universal programmable quantum computer and to identify the revolutionary applications that we are going to run on it, that are going to change the future. To do so, we do need software that is vastly different than the software that we have today. At Microsoft, we are working on building the complete quantum computing system. That is both the cryogenic computer on one hand, but also the entire software stack that allows to control and to program this quantum computer at scale. So today, what I'm going to be talking about is the work that we do at the top of the stack to enable developing powerful quantum applications. Like no other company in the world, Microsoft knows that great developer tools are fundamental for any technical leap forward. Whether it is Bill Gates working on a basic compiler when Microsoft was just coming into existence, or integrated systems like Visual Basic and Visual C++ that brought graphical user-face development into reach of programmers like us. Unlocking new businesses like consumer entertainment always requires both hardware and software, like, for example, the HoloLens development kit. And today, we're bringing the cloud platform, Azure, to developers with great client, web, and data center tools. As you see, helping developers make use of tomorrow's technology is deeply embedded in our DNA. Quantum computing promises to be another great technical leap forward. And our tools are advancing and evolving to meet the need of tomorrow's platforms. When we introduced the Quantum Development Kit in December last year, we took a holistic view of what it takes to be productive in quantum programming. And we built best-in-class solutions for every step along the way. We have, I believe, succeeded in creating one of the most comprehensible set of software tools that is available for quantum programming anywhere. The Quantum Development Kit is at the heart of Microsoft's quantum software stack. And it comes with our new quantum programming language, Q#. Now, Q# has been specifically designed for you to make it easy to express powerful quantum applications. Q# has the richness of a high-level language, and at the same time adds quantum-specific abstractions that allow you to express a quantum program naturally. Just like the C# compiler takes your code and translates it to what the conventional system you want it to run on needs to do, the Q# compiler does the hard work for you by taking familiar-looking code and translating it into instructions that a quantum computing device can execute. The Quantum Development Kit also comes with 2 powerful quantum hardware simulators. Now, Q# is fully integrated into both Visual Studio and Visual Studio Code. So you can use those simulators to work from within Visual Studio or Visual Studio Code to actually run, test, and debug your code, just like you're used to for any conventional computer. Now, unlike for conventional computers, it's usually a lot harder to actually debug a quantum algorithm. So having these tools available to you is invaluable. Step through your program, set breakpoints, or you can use our trace simulator to get real-world costs of executing your code on a quantum computer. I'm sorry. So with these tools, let the industry's brightest minds guide you when you write your very first quantum solution. There's a rich set of open source libraries that come with the Quantum Development Kit that teach you about how software development works for quantum computers. Written by experts, they are ready-to-use building blocks that provide everything you need for software development. And our libraries encapsulate common quantum programming routines and the quantum algorithms we've been developing for the past couple of decades. So let's talk a little bit more about Q#. I won't have time here to do justice to all the ways that we've actually tailored Q# to writing quantum programs. But if you're interested, there are also breakout sessions. So if you want more details, swing by one of those. But I would like to give you some key points as well before we proceed to a demonstration where I can actually show you Q# in action. Q# is an awesome language for exploring and experimenting with quantum computing. But what's more, it's designed to scale. So you can use it today to write a small quantum application that you can simulate and, more importantly, analyze on your laptop and really get an understanding of what it means to harness the power of quantum, where this power comes from. But you can also use the same setup or even the same algorithm to scale to million-qubit devices in the future. Q# is a strongly typed language, a high-level language, that also provides you the classical language constructs that we as developers have come to rely on, like for loops and array manipulations. Now, maybe you remember back in Michael's talk when he talked about the classical components and the quantum components that go into a full quantum computer. Having something like for loops and array manipulations may sound trivial and is something that we take for granted when we develop software for conventional computers. But the Q# language and compiler are very unique in their capability that they can both express and, what's more important, optimize both the classical and the quantum parts of your algorithm. Harnessing the power of quantum may seem like a daunting task. But Q# also comes with an arsenal of quantum-specific features that make it easier for you to approach this new field. For example, we have automated qubit management. And we have compiler-generated quantum-specific transformations. Now, memory management is something that we kind of expect from higher-level languages, that we don't need to worry about it too much. But consider just how scarce qubits are right now to work with. So having a good memory management is really fundamental and important. And also, it works slightly differently than in the classical case. So we don't want you to have to worry about that, because I have too much fun doing it. So in that sense, I'm not going to go into more detail about our quantum-specific features, like the transformations. If you're curious, again, there are breakout sessions. We do also provide, though, a large set of samples and documentation that help you understand and learn about these capabilities and to use them. So let's move to see Q# in action, shall we? Today, I'm going to give you a small demonstration using Visual Studio Code running on my Windows laptop. But as I've mentioned, the Quantum Development Kit runs on Windows, Linux, and Mac OS, and is fully integrated into both Visual Studio and Visual Studio Code. Using our simulators, you can test Q#-based solutions locally. I don't know how many of you do have a quantum computer in their basement. But I mean, if I did, I might spend less time at work and more time in my basement. So probably it's a good thing it actually runs on my laptop. You can utilize the included trace simulator to optimize your code and to calculate the cost of executing your program on large-scale quantum computers. So our tools give you the fastest path to quantum computing on every platform. So as you can see, aside from the comments, this should look pretty familiar to you. We have a couple of maybe more exotic-looking things, like these things here. These are basically directives for the compiler to generate certain transformations. For example, this adjoint of an operation here just means, please get me the routine that will undo whatever I did here. And you don't need to worry about how that is done, what it means to revert what you have written. And seeing as in quantum computing, it's a frequent occurrence that you do something, you insert a middle part, and then you undo what you did the first time for some subset of your system. This actually is a huge saver in productivity. It saves you writing roughly, it allows you to write roughly 25% of your code because the rest is automatically generated. You may also see that there are some familiar looking things. So we are heavily tuple-based. We have all the tuple deconstructions that you're used to from F# and C# 7.0. And we do have, for example, partial applications that return a new function or operation. So let me just quickly run this. As you can see, we're running on .NET Core, so anything I do here will run on Windows, Linux, Mac OS, whatever you want. And we're using the Electron package to actually visualize the output of your computation. So what I'm running here, I forgot to say, I apologize, is actually a computation of the energy for the hydrogen molecule for different bond lengths. And the gray part that you're seeing here are the results that are expected from theory, while the red line is what is computed using a quantum algorithm. Now, obviously, this runs here right on my laptop. I can assure you it's not going to the cloud, a high-performance cluster, some fancy hardware, or even a quantum computer. It's just running on my laptop. So what this uses under the hood is our simulator that fully simulates how a quantum system would behave. As Michael has told you, this obviously only works for a smaller number of qubits. You can simulate up to 30 qubits roughly on your laptop. After that, you can use our Azure-based simulator for larger simulations. But it gives you a starting point. And in addition to that, we have our trace simulator that will work for a much, much larger number of qubits. Because what that simulator does is it doesn't care too much about what a quantum system would do, but it only cares about evaluating performance metrics of your code. So it's counting what the minimal time would be that your algorithm would need to execute, how much qubits, how many qubits you need to execute it. Now, this becomes particularly interesting with more powerful optimizations as they are being integrated into the compiler, because what you are writing may not make it immediately obvious what that is, what these numbers and values are. So let me just quickly show you some of the handy tools. Obviously, these are tiny, tiny toy examples just to kind of show you some of the features. Here's a rather trivial example that allocates a bunch of qubits and kind of evenly distributes the state all over the space, as we've seen on Michael's slide, for example. So we can run this, and that's the nice thing now about being on a conventional laptop. Because with our simulators, you can actually get how your state looks like. Now, seeing something like that, here you see the uniform superposition. That is not something you could ever check or verify that you're producing this kind of state on your quantum hardware. It's pretty expensive and pretty hard overall to do these kind of verifications in hardware. those of you who have worked with embedded systems probably know that. It only gets worse for quantum. So in that sense, having these tools can be a huge help. You also see that we get some program specifications. I didn't output too many. There are a lot more than that because the example is pretty trivial, so there's not that much interesting data. But what we see is that 4 instructions have been performed simultaneously. Now, this is basically the time, the minimal time your algorithm would take to run. And these, for example, can be set as configurations to your trace simulator. So this 2 here is due to a measurement we do at the end. I had a time of 2 units set. If I set a time of 1, as I did now, as you see, you get a depth of 1. So I hope this has made you a little bit curious about what we are doing and what our software can do. Before we go, I would like to give you an update on what's next. Later this year, we are going to release an update to the Quantum Development Kit that will include significant improvements to the developer experience and also some language improvements. If you're curious about these features, stay tuned and watch for an update on our Quantum blog. The update of the Quantum Development Kit later this year will also include our new chemical simulation library that can help solve real-world chemistry problems using Q#. Michael talked about how quantum computers are particularly good at simulating other quantum systems because they can hold so much information, in a sense. And they can thus be used to possibly develop new materials. And one of the examples he gave was using quantum computing for developing cheap fertilizers. Our new chemistry library comes with an arsenal of quantum algorithms for simulating chemical processes on a quantum computer and for analyzing chemical properties. This chemical library has been developed in collaboration with the Pacific Northwest National Laboratory. I'm sorry, long name. And is designed to be used in conjunction with NW-Chem, an open source, high performance computational chemistry package and tool that has been developed, has been funded by the US Department of Energy's Office of Science. Together, Microsoft Quantum's Development Kit's Quantum Chemistry Library and NW-Chem will empower both researchers but also developers with a platform and a rich tool set when they tackle today's challenging chemistry problems. So now that you know what the Quantum Development Kit has to offer, I hope you are ready to start coding in Q#. To learn more about Q#, and in particular how to get started, please come to one of my theater sessions later on, where I will go into more details about Q# and about our quantum katas. There are awesome self-paced exercises that teach you both quantum computing and Q# at the same time. Join Microsoft's quantum community today and sign up at microsoft.com/quantum. I hope you're as excited as I am about being part of a quantum revolution. And as part of Microsoft's worldwide community, help us shape the future of computing. Thank you very much.
Any questions from the audience that we can field? Yeah.
So does the Q-Sharp toolkit come with error detection and resolution, or error detection and visibility?
So by design, if you're running onto something like the quantum simulator, it performs perfect computations in a sense. So there are different kinds of errors in quantum computing. On one hand, we have quantum algorithms by nature are usually probabilistic. So there's a certain amount of error that comes in because your algorithm is not designed to be deterministic fully. That, of course, you can fully look at. There are other errors, like hardware errors, potentially, that come in. And obviously, that depends on the hardware. And even the knowledge about how these errors are supposed to behave is kind of a tricky thing to figure out based on actual lab data. You could, of course, you can have a simulator that simulates that noise. But it's only ever going to be so accurate. And a lot of noise in quantum computing would require you to have too much memory, simply. You run out of memory pretty quickly. But on the small things, yeah, you could have experiments with that.
I have a question. So what is the current status of quantum computing? I mean, you showed a picture of a bunch of qubits refrigerated somewhere. So how close are we to breaking RSA, for example?
That's a great question. So there are various sizes of problems that we would like to tackle. And RSA is of the problems that we have talked about today, is one of the most far away. You really need a very big quantum computer to build, to crack RSA for 2,000-bit numbers.
So what do we have now?
What do we have at the minute? Well, I would say that across the globe, there are lots of different approaches to building qubits. All of them are pretty small, so we have quite small systems. All of the different teams that exist, both in universities and companies, are trying to scale up. Our approach at Microsoft is to build a system which kind of scales from the outset, where we have much lower noise, but we and no other team are yet at the stage where we have very large numbers of qubits. So I think the most qubits that anyone has, although they're quite noisy, are in the tens to hundreds, but depends on some of the qubits that exist out there are so noisy that some people would even argue about whether they could be called qubits or not. Yeah, but we can talk offline in more detail after.
My understanding is that with qubits, once you look at them, they sort of destroy. Like, you can't look at the state of it. So how do you know when the qubit has solved the problem, and then you can look at the state to see the answer? It's always been...
Yeah, that's another really good question. So the way that a quantum algorithm typically works is that you start the entire set of qubits in some very specific quantum state, which is actually more it's close to the classical state. A little bit like when we walked through the example of a qubit, you can have a qubit be in a 0 or a 1. So quantum algorithms will start with all of the qubits, say, being in the 0 state. And by the time you end your computation, the same thing will be true. The very last step of any quantum computation will be to measure all of the qubits and see what values they have. And actually, it's an art to develop a computer or a quantum algorithm that ensures that just before you measure the qubit state at the very end, you're actually in or close to one of these very conventional classical states, so that you actually don't just get random outcomes when you measure at the end. You should get something which is quite specific, which should tell you about the answer to your problem. Again, I'd love to tell you more about it afterwards.
Oh, yeah. One other question. I know there's a line behind me. But the other thing is like in computer science, there's certain problems that to test against to know that it's a computer. Is there like a known problem that all the researchers are using to say, oh, after I test this, I have a true quantum computer?
Another good question. There are known problems. There are known problems that we have very specific algorithms that we would know exactly what you run on hardware that you could in principle do, and you would know that they were getting the right answers. So from some point of view, yes, but I don't know that there's a good answer to the question that you asked, but yeah.
Well, you would have to specify what a true quantum computer is, because there's a whole lot that goes into that. Like, for example, if you have a specific way of actually executing your instructions on your device, and that scales with the size of your device, is that something you can live with? Is that good enough to be useful, or is it not? So,
I know what you mean, but it's sort of like the one more of the fact is like if you know the answer and you run it, and then you okay, all right, I got the right answer. Like when you start talking about global warming, all this other stuff, you don't know what the answer is, so
yeah.
you don't know if it's a lie or it's the truth, and that's why it's more.
I would say so. What I would say is there are definitely problems where if you could solve that problem, then we would all be convinced. You could, for example, have a quantum computer in your basement, as Bettina said earlier, that you don't tell anyone about or no one gets to see, and there are problems that you could send a person, and if they could solve them, you would say, okay, then I'm very convinced you have a quantum computer, because otherwise you couldn't have solved that. And one of those problems actually would be factoring. That would be very convincing if you could give someone a very large digit number. If they could factor it, you would be pretty sure they had a quantum computer. But saying that, that's not one of the early stage algorithms, so they need a huge quantum computer to do that. But yeah, so I guess that would be a case, but that's kind of a far out example. Sure.
Just a question about the qubits. I was just reading about it. So it's a two-dimensional braid at ultra low temperatures.
Sorry, it's quite hard to hear actually from this microphone. It's not.
Sorry.
It's not used the same for everybody.
With the qubits, topological qubits.
Yeah.
So it's a two-dimensional braid. Is the quantum state of that braid read through the magnetic field in that ultra cold state?
There are various different, so when people use the word topological qubit, that branches out into a bunch of different things. And the one that Microsoft are building, it's called the Majorana wire. It's a one-dimensional system. And that does not implement the gates or the storage through braids. But there's another branch of qubit, topological qubit, that would. But yeah, again, maybe it's kind of getting a little specialized for the group discussion, but we can chat about it after. But if you have another question as well.
No, that was it.
Okay, sure.
Hi. Are there some kind of problems that can be solved with a quantum computer, but can be solved with a classical computer?
Are there problems which can be solved with a classical computer, but not? So you're asking, are quantum computers strictly more powerful than classical computers, or is there some stuff that quantum computers are good for and some stuff? Well, this is, I think from a theoretical point of view, no. If you have a quantum computer with, let's say, n qubits, and you have a classical computer with n bits, quantum computer can do everything the classical computer can do. The kind of more realistic question is, well, we actually have classical computers, conventional computers, with many, many bits. Peta was the word that I threw around earlier. So millions of billions of bits. And if you have a quantum computer, which is small compared to that, there could, of course, be some problems that you can solve in the classical computer, but not the quantum, and vice versa. Does that make sense?
Yes, definitely. Thank you.
Cool.
So you had a slide where you had the conventional bits versus the qubits.
Yeah.
And there's a lot of sessions on artificial intelligence, and that's being solved with conventional bits. Is that going to be the next thing to move into qubits? I mean, do qubits, does quantum mechanics more apt towards solving a real artificial intelligence or building a real artificial intelligence?
I would say that the best answer I could give to that is that it's at the minute unknown. It's an active area of research, and it's not totally clear what the impact of quantum computing would be in the AI space, but it's definitely something that lots of people are thinking about, and it would be very exciting if we could get big gains there too.
So the thing is also that what we currently solve with machine learning or artificial intelligence are things that are well suited to do that with the tools that we have today. And having a quantum computer provides fundamentally different tools. So potentially this could open up a whole new branch of artificial intelligence or machine learning that today is not even in consideration.
This is actually a problem that comes up quite a lot. When you try and engage with a team working in a different area to see what are the problems that are really high value that you can't solve, that we may be able to improve with quantum computing, then it's actually tricky sometimes because the problems that they really understand and know about are the ones that they can solve. Those are the ones they work on. Why would they work on the things that are impossible? So yes, like Bettina said, it's kind of exciting to think about what can't be done in AI at the minute. It's not very well understood.
So qubit is a unit of storage. That means that we're also going to have problems with storing that and then some sort of way to process it. So are those the next steps? First, we have qubits as storage in a memory equivalent so that we can conventionally change them, and then the next step is to have a quantum processor that would process them, or are they being developed at the same time?
So we are thinking a lot about what it takes to actually make a quantum application work end-to-end, which I believe is exactly what you're asking. But wait, there's not just computing, there's also practical considerations, like where does my memory go? If I now want to load something, as we know from conventional computing, when I want to load something, then do something with it, put it back, where does it go, right? So again, quantum computing is slightly different in a lot of ways. For example, you can have scratch space that simultaneously holds part of the memory for some computation, but is not actively in use, that can then be used by another part of your computation to do stuff with it without actually destroying the information it held for the first part. So in that sense, there are a lot of problems that people have been working on in classical compiler construction that are solved really well, that are very similar to what we need, and we can profit a lot from that experience in a sense. But also there's a slight twist to it in quantum mechanics. And we're working on that today. Of course, until we actually do have the hardware to see if it does work in reality, we can hope for the best, we can design it, speaking more with the heart of an engineer, until you do have the device, you don't know. We can have plans.
Thank you. As long as I don't have to put in punch cards when I get my time on the quantum computer, I'll be good.
Exactly.
Yeah, that's definitely what the QDK is, or one of the things the QDK is trying to avoid.
I'm sort of oversimplifying what I understood, right? But can quantum computer be seen as, let's say, a faster computer? Let's say I have an algorithm that takes 2 hours to run, that simulates something, right? If I write that same algorithm in Q# using quantum-inspired algorithm, will that be any faster, or can it be seen that way?
No. That's a simple answer to your question. But so the idea is, yeah, first of all, quantum computers, you can't take a classical algorithm that runs on a conventional computer and just plug it into a quantum computer and get a faster algorithm. So that's the first thing to say. You would actually have to come up with an algorithm which worked differently, that was able to take advantage of the quantum effects in some way. And there's an art to that. And again, that's another advantage of the quantum development kit, is that the academic community and people in our team have developed those kind of subroutines that take advantage of the quantum parts and allow you to call those. You might know what it does, but not necessarily know how, and call those things. So you could rewrite your algorithm and take advantage of some subroutines that run quantumly and do some things quicker to get a speed up, but you wouldn't just run exactly the same algorithm.
So what you said is potentially there is a subset of classical algorithms that could benefit from being rewritten in Q# and using the quantum-inspired algorithm.
That's right, yeah.
Yeah, though, I mean, as long as you run it on classical hardware and simulate it, the simulator is really a tool to give you insight into what goes on in a quantum system. So you're not going to see a speed up when you simply run it on your laptop. It's still doing the classical computation. You might see it, I mean, purely based on the algorithms being so much stronger than when you're using. But that's then going towards quantum inspired.
Makes sense. Thank you.
Any other questions? You finish up? Okay. If anyone wants to chat in person after, that's fine too.